So today we're going to look at some more applications of the time-dependent Schrodinger equation. As you all know, the time-dependent Schrodinger equation is given in this succinct, nice, compact form. The time derivative of a quantum state, which by the way is an object that lives in a quantum space. We don't see it on its own. We only see the impact of this quantum system, of this quantum state, when we look at its overlap with different measurement basis vectors. And this equals this operator acting on the quantum state itself. This operator, as you know, is the Hamiltonian, and it corresponds to energy of the system. The Hamiltonian and the energy, and when we solve this equation, we get how the state changes with time. So at some point in time, the quantum state is psi 0, and this changes with time in the quantum space. For a qubit, it's the Bloch sphere. It changes with time, and after some time you end up at another location, at another point where the quantum state has evolved into psi at some time t. And all of this action, this drama, takes place on the Bloch sphere, in which the two cardinal points at the north and the south pole are ket 0 and ket 1. This state at some later time t is nothing but the solution to the time dependent Schrodinger equation. So, and the solution goes as follows. You take the state at time t equals 0, and upon this you act an operator which is unitary, and that operator is given by E minus iota, the Hamiltonian, into times divided by h bar. And we've also seen that for a spin inside a magnetic field, the Hamiltonian can take up forms which are proportional to the Pauli operators, and then we can get all kinds of revolutions and rotations on the Bloch sphere. So this is what we've learned so far. So far everything is looking good, very nice. Let's look at some more applications so that this idea is consolidated a bit further. The first application that we've already seen this in disguise, is this idea of Rabi flopping. Rabi was, of course, another Nobel laureate. So suppose I have a proton inside a magnetic field, spin half particle, and what I do is, now I'm going to draw a diagram which is very kind of commonplace in quantum computing, and this is how you design your quantum computers. I'm going to draw a pulse diagram. So the pulse diagram goes as follows. I have time on this axis, and on the vertical axis I draw magnetic fields. So what I do is I switch on a magnetic field at time t equals 0, keep it constant for some time capital T. So this is a magnetic field that's 0 before time 0 and after time capital T, and the strength of this magnetic field, say, is B, and it's pointing in the z direction. All right. So the field is important. Which direction is the magnetic field pointing in? So it's parallel to the z direction. The strength of this field is B. Now I have a spin inside my quantum processor, and I switch on this magnetic field. I want to see how it evolves. So this is my pulse diagram, which shows how the field is going to change with time. Now what a quantum engineer would do is he or she knows what his quantum computer is like. He knows that the qubit is now a spin inside a magnetic field. So in order to change the state, in order to do a computation, a transformation, he or she would need to design a pulse sequence, a sequence of magnetic fields. So this is a very simple magnetic field that is merely switching on and off. Suppose my initial quantum state psi naught is ket 0, which corresponds to a spin which is pointing in the direction of the magnetic field, parallel to the magnetic field. Alright, I also assume that my field is pointing along x. Suppose it's pointing along x. So here is my cartoonic configuration. I have a spin which is pointing in the direction of a magnetic field. The magnetic field is up. This is my magnetic field B pointing along, sorry, my magnetic field is pointing along the x direction, B parallel to the x direction, but my spin is pointing up, it's in the z direction. Alright, so the field is perpendicular to the magnetic field. So the idea is that at some point back in the history of this spin, a magnetic field along the z was applied, which kind of oriented the spin along the z direction, and then that it stayed there, and the field at some point in time switched off, and later in time it was switched on in the x direction. So I have to initialize my spin somehow back in time, so it's in the z direction, and the z direction spin is denoted as ket 0. Anti-parallel is denoted as ket 1. So these are my 2 points on the block sphere. So if I were to draw a block sphere, initially this is where my spin is pointing in along ket 0. This is my initial spin, and now I've turned on a magnetic field in the x direction. In the block sphere, this x is pointing towards me, right? It's towards you, in fact. This is the configuration. So now, before time t equals 0, this quantum state is going to live in its native state, ket 0. Nothing is going to happen. There is no Hamiltonian. There is nothing that can change the quantum system. So it's initialized at ket 0 state. Now the magnetic field is switched on. So this quantum state, which is represented by a blue vector on this block diagram, is going to change. It's going to evolve with time, and the time dependent Schrodinger equation determines that evolution. Therefore, we already know that we can describe the evolution by this unitary operator u, which is E minus I. Since the field is pointing along the x direction, I can write a Hamiltonian. That Hamiltonian is h bar omega over 2. Now this field is in the x direction, so I need to apply a Pauli operator in the x direction. So it's going to happen like this all the time. You need to determine the direction in which the field is applied and apply the corresponding Pauli operator inside the Hamiltonian. If it were applied along the y direction, you would have y operator here. Z would have z here. Omega captures the magnetic field, the strength of the magnetic field, because omega, as you've learned, is given by minus a constant, the magnetogyric ratio times the magnetic field. So this frequency depends upon how strong the magnetic field is. Now with this Hamiltonian, our time evolution is going to be determined by the solution to the Schrodinger equation. It's going to be given by minus I h bar omega t over 2 h bar x. This is my operator. So the h bar luckily goes away and I'm left with this. So the square of x is identity. So I can apply my theorem here. My theorem would tell me that all of this will be inside a cosine and a sine factor. So this will become cosine of omega t over 2, identity. I put a hat on top of identity. It's not 1, it's the unit matrix. With this minus iota, I get minus iota sine of this number omega t over 2x. Now I know what these matrices look like. So far so good. I can also write this in matrix form if I were to desire so. So in matrix form, this operator looks like the following: cosine omega t over 2. This is x, so I get minus iota sine omega t over 2 minus iota sine omega t over 2 cosine omega t over 2. And now this acts on my quantum state. My quantum state is ket 1 0. So if I were to do that calculation, u acting on my initial state, this will be the state at some later time. Now there are different ways in which I could do this. I could do this by writing out the matrix forms, or I could do this directly with just the ket versions. But let me do the complete matrix calculation. This is cosine omega t over 2 minus iota sine omega t over 2 minus iota sine omega t over 2 cosine omega t over 2 acting on my initial state, which is simply ket 0, and this gives me cosine omega t over 2 and minus I sine omega t over 2. And if I were to write this again in ket form, this will be cosine omega t over 2. Can you complete my sentence, please? Ket 0 minus iota sine omega t over 2 ket 1. This is how the state is going to change with time. And after time capital T, it's going to stop there. So at time t equals 0, capital T, this state is going to stop at some point. I just replace small t with capital T. It's going to stop here. Now let's look at this evolution on the Bloch sphere. Right? How does this state change on the Bloch sphere? Now on the Bloch sphere, there are different ways to look at it. The first thing is that every single qubit gate, every single qubit transformation is a rotation on a Bloch sphere. Every single qubit gate is that. So it's a rotation on a Bloch sphere. We need to define an axis of rotation, and we need to define the amount of rotation. So the axis of rotation is simply given by this x, so it's along the x-axis. And the amount of rotation is, how much is the amount of rotation in time small t? Not omega t over 2, it's omega t. So this is that slight thing you need to remember. it's omega t. So now this is my initial state, this is my axis of rotation. Okay, let's do it like this. My axis of rotation, my initial quantum state, I want to rotate about this axis. So this is kind of my fulcrum, my needle of which doesn't change, and this state in an anti-clockwise fashion from your perspective goes towards the equatorial plane. Keeps on going until the field switches off. How fast does it go? It depends upon omega, depends upon the magnetic field. So if this keeps on going, it just goes round and round in circles. So at some later time, if this were my kind of y-axis, this were my minus y-axis, this were my y-axis, just hypothetically, these are not x, y and z, but these are quantum states. So this state, which started off in blue on the Bloch sphere, is now going to go around on a big circle towards the minus y-axis. So with time, it's going to come down, come down, come down. Eventually, it might get to the equatorial plane. When that happens, omega small t, omega t is given by pi by 2. So it's a 90 degrees rotation, right? If this keeps on going, it goes down to the southern hemisphere, and it all depends upon where this pulse ends. When it ends, it just stays there because now the field is switched off. So if for example omega t were pi by 2, I would have ended up at 1 over under root 2. I just insert pi by 2 here. I'll get ket 0 minus iota ket 1 over under root 2. That's this point over here. Okay? Then such a pulse is called a 90 degree pulse. That's a 90 degree pulse. So then the pulse is a 90 degree pulse. So modern day quantum computers that you can find for IBM, etc., they apply these 90 degree pulses. Though they do not deal with spins of protons, they deal with other superconducting quantum interference devices, but it's the same idea. Exactly the same mathematics describes those quantum computers as well. The working systems are qubits, two-level quantum systems, though physically they are different, but the mathematics, the language is generic. They're described by the same kind of pulses. A pi pulse is when omega t is 180 degrees. So when that happens, this becomes cosine of 90, which is 0, minus I sine of 90, which, so you end up with minus iota ket 1. Where does this state lie on the Bloch sphere? Does it lie here? It lies here because this point is ket 1. So you can multiply this with any phase factor, any iota, plus iota, ei, theta, anything, it just remains there. It's the same point because this global phase doesn't really matter. Okay, so this point is proportional to ket 1. We just apply any global phase factor to this point is represented by this point. So this is a pi pulse. So you've seen a consistent view here. Now if I had a system which could detect the probability of projecting this quantum state on a detector that is aligned with ket 0, I will get something. So if I take this quantum state here and try to measure it along the ket z direction, a ket 0 direction. So how do you measure spins? You can have some kind of sensors that can look at magnetic fields. For example, coils. But I'll come to that in a minute. So if I were to take this quantum state and measure it along cat 0. This is my overlap. This is my inner product. The probability that I measure along 0 is the modulus square of this. Correct? And what is that probability going to be? Cosine square omega small t over 2. Likewise, the probability to measure along cat 1, this is going to be minus iota square is 1, right? Just be sine square omega t over 2. So this process, so if I were to make a graph with time of the probability p naught, it's going to be a cosine square function. It's going to look like this. So the spin, so if you interrupt your system, at time capital T and then you make a measurement on cat 0, you'll end up somewhere on this graph, here, here. Suppose I end up, my time capital T is this much. So I end up here. This will be the probability of detecting my spin along cat 0. The detector along cat 0 is going to click. All right. Okay, so this is how this more or less works. So if I were to plot P1, P1 is a sine square function, so it's going to have a complementary probability. This is P1. At any time, the sum of these probabilities must be equal to 1. That's the conservation of probability. So this kind of process in which you apply a magnetic field to a spin, the magnetic field is perpendicular to the spin, and you see a flopping effect from cat 0 to cat 1. So there's an inversion of the quantum state from cat 0 to cat 1, and the inversion keeps on happening. It's a population inversion. This is also called population inversion. If you have many spins, all of them start off identically. All of them will be in the state cat 1 after a 180-degree pulse. They will return back to cat 0 after a 360-degree pulse. So this flopping is called Rabi flopping. So when you design a new quantum system, this is the first experiment you would do. You would see the existence of Rabi flops. The system is going to oscillate. And what's the frequency of this oscillation? It's omega. So this time period is omega. That shows you the frequency at which the spins are going to oscillate between cat 0 and cat 1. So this is the idea of Rabi flopping. By the way, one interesting argument one could make is, before I tell you something interesting, do you have any questions about this? So if I were to detect, can I possibly in the physical laboratory detect a precessing spin? Precessing means rotating spin. I would like to remind you, yes? Exactly. So if this is a precessing spin, what I could do really is place a small coil. So just hypothetically, if I were to place a coil oriented along the z direction, this spin is going to kind of precess. So the flux from this spin, it's a tiny magnet. You all know it's a magnet. The strength of this magnet is called the dipole moment. This flux is going to kind of pierce this coil. And when a changing flux passes through a coil, what happens? An EMF is generated. a voltage is generated. That voltage, if this circuit is connected or connected to a voltmeter, it's going to give an oscillating voltage. That oscillating voltage will have the same form, slightly different than this voltage, but it's going to have the same period. In fact, it's also possible to calculate this voltage, but I think that's beyond the scope. You use Faraday's law to look at the derivative of the signal and you get the EMF, but you can measure using coils. That's what happens in an NMR spectrometer. In an NMR spectrometer, you have coils that look at these spins and they give a signal. Very similar to this. Not exactly, but very similar to this. And then you look at the frequency of this signal and that gives you a spectrum. So when you have a time domain signal and you convert it to frequency, you get a spectrum. So now this is a concept that probably you're going to use later. So you have a signal that changes with time, like say a sine function. This is my time axis. If I were to plot this signal, the same signal on the frequency axis, I can do that. So this signal will have a certain frequency. 2 pi over omega is going to be the frequency of this signal. So the time period is 2 pi over omega. So if this were a nice sinusoidal signal in time, it's going to have a frequency omega. So I can plot the entire signal on the frequency axis. Now this signal will have a peak at, so this is omega naught, this will have a peak at omega naught because it just has one frequency. In fact, it's also going to have a peak at minus omega naught, but that's slightly more technical stuff. So this kind of spectrum, this is a spectrum which shows the signal in terms of frequency. It's called a spectrum. That's what a spectrum means. This is a spectrum. You can go from here to here and you can go back from here to here through a technique called Fourier transformation. Probably you learned this in some course. So through the technique of Fourier transformation, you can go from time to frequency. Have you studied Fourier transformation in any other course? Not yet? Okay. Anyway, so this is the idea of Rabi flopping. Now let's do interferometry with these spins. Questions? Yes, please. Magnitude. Because there's just one frequency. Just one frequency, so this is actually a Dirac delta function, just one point. Its height is infinite. Time is 0, height is infinite, so the area is 1. It's called a Dirac delta function. Anyway, any questions about Rabi flopping? Sorry? Isidore Rabi, the name of the person. Yes, please. Yes. So no.
Are we talking about it in terms of like an electron in a magnetic field whose spin keeps flopping in different directions? But how does that work? How does it come from the low energy state back to the high energy?
Right. So first of all, it can be an electron, it could be a proton, it could be a neutron, it could be any spin half particle. All right. So you're giving it energy. So that energy is coming through the magnetic field. That magnetic field, it can be assumed that this electron has a quantum state that is going around between on a Bloch sphere. It's making this entire circle. Starting from here, goes around, keeps on going around on this circle. One of them is the low energy state, the other is the high energy state. You can imagine this if you were to kind of particulate minded or quantum minded, you can imagine that it is constantly emitting photons and absorbing photons. So it's in a radiation field and it's continuously absorbing photons and continuously re-emitting them. It's in a state of equilibrium with the bath of photons around it. Okay, so it's related to the idea of spontaneous emission as well. All right, now the next example I would like to give to you is, can we do interferometry with these states, and can we employ the time dependent Schrodinger equation in understanding interferometry? We've seen interferometers, so let's try to do interferometry. And so whenever you start learning atomic physics, how do atoms behave, how do molecules behave, how do they interact with light, with magnetic fields, this is the first example you learn about Rabi flopping. So this is your preface to atomic physics as well. So now let's do interferometry, and let's build an interferometer in time. All right, so I'm going to talk a little bit about Ramsey Interferometry. If you look at your conventional Mach-Zehnder interferometer, deals with polarization or path of photons. So the system looks like the following. You have two beam splitters, two mirrors, and a photon comes in a particular path, gets 0. Suppose I have a detector here, D1. So if I were to make a quantum circuit for this, interferometer, what kind of quantum gates do I need to apply? What does the beam splitter represent? Hadamard. So if I were to draw a quantum circuit, first of all I apply a Hadamard gate, followed by, there's no NOT gate here so far. So suppose I would like to, if I were to do interferometry, I would like to introduce a phase. Suppose I have a phase here introduced. I put in a piece of medium that imposes a phase. So suppose the mirrors really kind of do nothing to both arms, they're just the same. So how can I represent a phase medium? By a phase gate, some kind of phase gate. A NOT gate is also a kind of a phase gate, by the way. So then I have a phase gate, U phi, followed by another Hadamard gate. So this is my interferometer. This is what it physically looks like. It's also a qubit. So I'm dealing with two-level systems, the path of a photon, physical picture. This is what it looks like physical to the human eye. This is what it looks like to the algorithmist, to the person who deals with quantum circuits, quantum algorithms. Now, can I also apply the same idea of pulses and pulse diagrams and spins inside a magnetic field? I need to do something of that kind, and I need to do interferometry. So where does interferometry come in here? If I were to look at the probability that detector D1 clicks, I will get some fringes. This is the probability that detector D1 clicks. What's on the x-axis for this diagram? Phi. Shabash. So there's some phase here. So this is interferometry. If I were to put a screen here instead of a detector, and these beams were slightly divergent, they were not kind of going in straight lines, they were slightly divergent, I would also get a pattern in space which looks like fringes. So if I were to put a screen here, I will get these bright and dark patterns. So this is my interferometry. But this is interferometry in phase. Can I do interferometry in time? That's what Ramsey interferometers mean. So what I do, What I would like to do now is I would like to kind of draw a pulse sequence diagram, a pulse diagram for a spin inside a magnetic field. And I would ask you to work your way through how the state changes with time. And can I get these interferometry fringes? So let me draw the pulse diagram first. Once again, I have a spin inside a magnetic field. Time. Time. My initial quantum state is cat 0. So I start off with cat 0, which is the low energy state, suppose. When you do quantum computing, you always have to start your quantum bits, your qubits, in some state. That's called the initial state. Every computer program has an initial state. Every flow chart you make has an initial kind of state. So now let me draw a pulse diagram. Suppose this is my time t equals 0. This is my time t equals 0. This is my point at which time t equals 0. First of all, I apply a field along the x direction. This is, let's call this Bx. I apply a magnetic field along the x direction. And I time this field, it goes on and off. And I time it such that omega into this time is 90 degrees. So I apply a 90 degree pulse. So this is a 90 degree pulse. You get this? So I apply a 90 degree pulse along the x axis. When this field switches off, I apply another field along the z direction. Let's call this Bz. And this is applied for a time tau. All right. And then when after this time tau goes out, I apply another pulse along the x direction, but actually along the minus x direction. So this is also a 90 degree pulse, but it has magnitude Bx, but it's in the opposite direction. So yes, please. नहीं टाउ है, बस कोई टाइम एंड टाउ, कोई भी टाइम एंड टाउ हमें नहीं पता जी. So if I were to take this omega corresponding to this Bx and multiply this with this time, this will be 90 degrees, pi by 2. So I apply a 90 degree pulse followed by a field along the z direction, followed by a 90 degree pulse in the minus x direction. Now first of all, there are multiple ways in which you can do this. First of all, you can do the entire solution to the time dependent Schrodinger equation, but let's do this intuitively. Now you understand block spheres. Let's try to do this diagrammatically. What's going to happen diagrammatically? This is my block sphere. I start off here, ket 0 is 0. This is where I start. Now on your notebooks, I give you a couple of minutes for this. Can you please plot the approximate trajectory from this pulse sequence? So this is my x direction. My x direction is pointing out towards you. I need to apply a 90 degree pulse. What happens in a 90 degree pulse? Where does this state come to? Negative y. Yes. जल्दी I think we'll finish a bit early instead of having a break. Is that okay? So what's the impact of the first 90-degree pulse? Where does the state end up after the first 90-degree pulse? Equatorial plane, which direction? Minus phi. So this is my axis of rotation. My state 90-degree gets me here. So I end up here. Let's call this point 1. This point here, the quantum state at 1. This is point 1. So the quantum state at point 1 is 1 over under root 2 ket 0 minus iota ket 1. Correct? Now what happens in the presence of this magnetic field which is pointing now along the z direction? So now I have a field in another direction, the z direction. So this is my quantum state and this is my axis of rotation. What's going to happen? What's going to happen to it? Right, it's going to move in the azimuthal plane, in the equatorial plane with a certain frequency that depends upon the strength of this magnetic field now. Going to move around in a circle in the equatorial plane for some time, which is tau. Tau pe aake ruk jayega. So this state is now going to fan out. It's going to move. Suppose I end up here. This is my new quantum state at time 2. Let's call this time 2. This point is time 2. Now how can I find this psi at time 2? So this is just advanced by omega tau, right? So I need to adjust the phase. The phase here is, what's the phase over here? This thing is really E minus I pi by 2. So the phase really is minus pi by 2. Now I add some phase to this. How much is the phase that, how much is this phase, which is this angle? Omega tau, where omega now depends upon Bz. This will have its own omega and this will have its own omega. Keep that in mind, because there are different fields. So let's call the omega corresponding to this as omega naught. Let's call omega naught is gamma Bz. Let's call this omega naught. So this additional phase is omega tau. So now I can just it's straightforward, just a matter of choice to have a new phase which is E. This was the old phase, minus pi by 2, plus omega tau, ket 1. This is simply minus iota E I omega tau, ket 1, ket 0, 1 over under root 2. Okay, so this is the quantum state at time 2. Got it? After, it might end up here as well if I adjust my tau good enough. It might even overshoot and go to the other side, to the eastern hemisphere. It might keep on going around and around. It depends upon how big a field I apply and for how long along the z direction, right? Suppose I end up here. So if I look at my trajectory and I plot my trajectory in pink, I'm just drawing now the locus of the tip of this block vector. I started off here, I come here, end up here. The first 90-degree pulse ends at that point in time. Then I apply another magnetic field along the z direction, end up here. Now the z field terminates. Now I want to apply a 90-degree rotation about the x-axis, but actually about the minus x-axis, which is like a minus 90-degree rotation about the x-axis. So where will this state end up now? It will go right here. It won't go, sorry, it will not go down. It will go somewhere here, right? It will just kind of goes end somewhere here. So it comes down to the equatorial plane, end up here. Now I want to do a 90-degree rotation for this axis, like this. It will end up in the xz plane. And what I could do is I can actually find out the new quantum state. I can also find out the new quantum state. How can I do that? I need to find the unitary operator for this thing. Let's find out the unitary operator for this thing. So let's call that unitary operator U3. It's E minus I. The angle of rotation is pi by 2. And the axis of rotation is the minus x-axis. So I put x over 2 here, but with the minus sign, which will make this positive. Okay? Got it? Because a 90-degree rotation about x is given by the amount of rotation into poly divided by 2. Right? So I can now write down this in matrix form as cosine of pi by 4 identity plus iota sine pi by 4 x. Got it? So this is my unitary operator for this pulse. Now this would act on this quantum state. Now one way is to write this in matrix form. Write all of this in matrix form. Write this in vector form and have the matrix act on the vector. Right? That's, I think, what most of you would do. And it's a legitimate thing to do. But it's also possible not to do that. We could really not do that as well. So our unitary operator U3 is 1 over under root 2 identity plus iota x. Correct? Now when this U3 acts on psi at 2, I get psi at 3, and that's 1 over under root 2 identity plus iota x acting on this ket over there, which is 1 over under root 2 ket 0 minus iota e I omega tau ket 1. Correct? So far so good? It's all making sense, isn't it? Any kind of ambiguities about it? I could do matrix calculation, that's all right, but I chose once in my lifetime not to do it, so that I can show you the variety of ways in which this problem can be solved. So this becomes 1/2. Now identity acting on all of this is the same state, ket 0 minus iota e I omega tau. Now I want this iota x to act on this. Now what is x? X is the poly x gate. It's actually a NOT gate. It's actually a NOT gate. So I can have the NOT gate act on this. But I need to take care of this iota. So x acting on ket 0 will give me ket 1. So, but I have this iota. So plus iota ket 1. Sorry, ket 1 plus iota ket 1 minus iota square is plus e I omega tau. X acting on ket 1 is ket 0. Got it? So far so good. So let's do some factorizations. 1/2. Let's look at the factors ket 0. Excuse me, please be attentive. 1 plus e I omega tau ket 0 plus iota 1 minus e I omega tau ket 1. This is my quantum state. Can I write this in a more kind of nice, friendly fashion? Yes. So what I would like to do, I would like to convert this. Now this answer is correct. Get 100 marks for it. But I would like to expose the physics to you. So, and I would like to expose interferometry concepts. So what I could do is I could write this in cosine and sine form. How could I do that? Yeah, I could take out something common, half e I omega tau. I could bring this out of the entire thing. So I'll get an e minus I omega tau here. Plus e plus I omega tau is 2 times cosine omega tau. So I'll get a 2 cosine omega tau ket 0 plus this iota. I get a minus 2i sine omega tau from here ket 1. This is just algebra. I mean, so this 2 goes away and I am left with, let's write this down in glory, big form. My final state is e I omega tau, all of this with cosine omega tau ket 0 minus iota square is plus sine omega tau ket 1. First of all, questions? Does this thing matter? No, it's a global phase. It's with all of it. It doesn't matter. Second, is this state normalized? It's normalized because the square of this plus the square of this is 1. So we have not kind of lost normalizations anywhere. And when you do rotation matrices, you don't lose the normalization. You just move on from one point to another point on the Bloch sphere. So this is a normalized state. And on the Bloch sphere, if I were to draw another Bloch sphere, where would this state lie on the Bloch sphere? So this is my x-axis. So I draw my Bloch sphere and I draw a slice on the xz plane. Where does this state psi 3 lie on the Bloch sphere? Which arc? This one? It lies on the 0 degree GMT line, which is really 0 degree longitude. It's on the xz plane. So if I were to draw an xz plane, this is my x-axis, xz. All of this is my xz plane, right? This point psi 3 lies on this big arc, big circle. So I started off here, came down here, moved on the equatorial plane, and then ended up here. So I'm here. Can you tell me what this angle theta is going to be by looking at the quantum state? What is this theta going to be? You look at that quantum state, look at how you represent general states on the Bloch sphere. What is this theta?
Pi by 4?
Pi by 4? No. Yes? नहीं आप यहाँ पे एंड कर रहे हैं, यू नॉट गोइंग ऑल द वे हियर. तो ये 90 डिग्री रोटेशन अबाउट दिस एक्सिस. So this, okay, let's look at the choreographics here. This spin is really making a kind of a dance on the Bloch sphere. Start off here, y, move here, move back. So let's look at this 90 degree rotation of this axis. My state is here on the equatorial plane. A 90 degree rotation ends me here. I don't go all the way up, I end up here. So it's on the xz plane, right? So I know what the quantum state is. I just am asking you a very kind of innocent question. What is this angle theta?
Pi by 2 minus omega naught.
No.
Omega t minus rho omega naught.
No. A general state at some theta on this big circle is cosine theta by 2 cat 0 plus sine theta by 2 cat 1. This phase, by the way, here is 1, right? This is 1. So by comparing this with this, it immediately transpires that this theta is 2 omega tau. All right. So you end up at this point on the Bloch sphere. Now where does interferometry come in? If I were to kind of take that state, quantum state psi 3. So I do this pulse sequence. What is my pulse sequence? Excuse me. What's my pulse sequence? 90 along x, some time along z, and minus 90 along x. 90x, some time along z, minus 90x. That's my pulse sequence. That time tau is my kind of my variable. I can change that in each experiment. So if I look at that quantum state which ends up psi 3 and I want to find the projection on cat 0 and take the modulus square of this, what is this going to look like? What's the projection of this on cat 0? Modulus square. What's the answer? cosine square omega tau. Now this is interferometry. This is an oscillatory function with time. If I were to plot this with time, let's call this P Ramsey, a Ramsey probability. P Ramsey, this probability, I'm just giving it a name. Ramsey was another Nobel laureate. If you plot this probability versus time, it's going to be a cosine square function. And this time is 2 pi over omega. So depending upon, so you do another experiment. So in one experiment your time is this much, you end up here. In another experiment the time is this much, you end up here. So you can do interferometry in time. You can change the time and get these fringes in time. So this is what is called Ramsey interferometry. Now the third example I would like to give. Any questions about this calculation here?
So what does fringes in time mean?
Fringes in time means that if you were to repeat this experiment, so you do one experiment. In the next experiment you change this time. So let me show you how you do that. Any other questions? By the way, I'll answer your question in a minute. By the way, this is your normal interferometer. This is our Ramsey interferometer, interferometer in time. Do you notice any similarities? Yes. The Hadamard gate sandwiching a phase gate. Here we have a kind of a pseudo Hadamard gate. It's not a real Hadamard gate, we've already learned that. It's a kind of pseudo Hadamard gate, 90-degree rotation. Hadamard. That's what a Hadamard gate does. This is also a 90-degree rotation that brings you back from the equatorial plane to the kind of ket zero state. That's what a Hadamard gate does. So these two are pseudo Hadamard gates, and in between you have a time which kind of determines the fringes. Here you have phase that determines the fringes. Here you have time that determines the fringes. How long do you let the spin precess in the presence of a z pointing magnetic field? So that's the analogy. This is an interferometer and so is this. So that is what is meant by time interferometry. So you repeat the experiment. If you want to get the entire graph that I've drawn over there, you have to repeat the experiment many times with variable times. You increment the time in each go. Okay? Now, what I would like to ask you is, in a real NMR experiment, in a real NMR experiment, which is commonly done with liquids, which chemists use, which is just round the corner, an NMR spectrometer. Let me draw a pulse sequence, and I would like you to kind of give me the intuitive block sphere picture of how the state changes with time. So the pulse sequence goes as follows. This is my time t equals 0. I apply a field along the z direction, Bz, and it's a large field, and then at some point later in time, after some time, say t prime, I apply a tiny field for some time capital T, along the y direction. This is what happens in a real NMR magnet. So in a real NMR magnet, it's very hard to switch on and off magnetic fields, because when you want to, if you have a coil, how do you produce magnetic fields? You have coils and a current goes through these coils, and those currents produce the magnetic field B. This is the best method to produce magnetic fields in a controllable manner through electricity. So if you have a large field, which means you really need a large current to go through the coil, and when you switch it on and off, current switching on and off, they are bad, because when you immediately switch on and off current, sparking could occur. It could be a fire hazard. It could emit electromagnetic radiation which affects other instruments. So you don't want large magnetic fields to switch on and off. So you want them to be on all the time. You want a magnetic field which is large to be on all the time, perennially, hamesha ke liye. Now can you think of such a system, which means that you need to have the current go on and on forever? So is there a kind of cool way of getting large magnetic fields, large currents, large battery, no load shedding? Is there a cool way to do that? You use a coil that is made up of a superconductor, which has zero resistance. It just has to keep it very cold, because a superconductor is only a superconductor when it's very cold, below a transition temperature. So if this coil were made of a superconductor which has zero resistance, you once connect it to the battery, have a current go through it, remove the battery, the current is going to persist forever. It's not going to die down, because the resistance is zero. The only thing is that you need to keep it really cold. So you need to keep on bathing this coil with liquid helium or liquid nitrogen. All right. So once you have this current going on, you don't want to switch it on and off. So that's why you want a large magnetic field along the z direction, and it's always on, always on. You don't want to switch it off. So if on the Bloch sphere your initial quantum state is ket 0, and you're somewhere over here in the system, somewhere over here, is this state going to change with time if it sees a z pointing field? No, because the axis of rotation is z and the state is also along the z. So no rotation, it stays there. But the moment you switch on a tiny magnetic field with the help of a tiny coil at room temperature, you make current go through it, so it produces a magnetic field along the y direction. And it's really small. If this were a Tesla, 1 Tesla, this would be 1,000 times smaller, perhaps a millitesla. It's easier to control small magnetic fields. You pass a current through a coil, it produces a small field. It's not a superconducting coil, it's a normal coil. Now, can you kind of predict on the Bloch sphere, no kind of mathematical calculation, can you predict in this location, somewhere over here, when this magnetic fields, both of them are on, but there's a large z field and a small, tiny weeny y field? What is the trajectory going to look like? So can you plot the trajectory? So what's going to happen? So what is this field going to do? Suppose there were no z field. What is this field going to do? It's going to bring it down at high speed or low speed? Low speed, because the y field is small, so it's going to come down. But when it slightly comes down, it still sees a large z field. Now the state is not parallel to the z field because it has been nudged down. Then what's going to happen? It's going to precess. It's going to precess, but the y field is on. So what's going to happen is that it's going to precess, but it's going to come down and down. So it's going to take a spiral motion. And while it comes down to the equatorial plane, it has made many thousands of more passes around the z axis, because that field is 1000 times larger. So it's not going to come down neatly like this, it's going to come down. So this, if I were to plot a trajectory going to the back of the circle, this is what's going to happen. So this is what happens in a real NMR experiment with liquids. This kind of combined motion along the z and the y-axis is called nutation. Okay, nutation. So this is what happens. So by the way, what's the axis of rotation here? Is it the z-axis or the y-axis? It's a combination of z and y. It's a so it's neither z, it's neither y, it's somewhere kind of in between, but close to the z-axis. Why close to the z-axis? Because this field is larger. If there were no z field, it would have been at the y-axis, but not very close to the z field, because the z field is much larger, but it's not at the z field. That's why it's going to be able to come down. Another kind of experiment which won a Nobel Prize, a pulse sequence that won a Nobel Prize, is the spin echo. Now the spin echo, why did this win a Nobel Prize? Because this led to the development of MRI, magnetic resonance imaging. With the help of this sequence, you're able to do magnetic resonance imaging with a high sensitivity, MRI. That's why you're able to diagnose cancers, that's why you're able to diagnose maladies in the soft tissue. What the spin echo pulse sequence looks like, sorry. So here I am plotting the field along the x-axis, here I am plotting the field along the z-axis. And I am doing a simplified version of the spin echo. I am not assuming that the z field is on all the time, because that's more complicated to understand. So what happens is the field is always pointing along the z-axis, along cat 0 to start off with, because that's the equilibrium state. That comes from thermodynamics. It always points in the parallel to the z-axis. Suppose, first of all, you bring it down to the equatorial plane, right? How do you do that? 90-degree pulse. You apply a 90-degree pulse along the x-axis. So, right, so apply a 90-degree pulse along the x-axis. I call this a 90-degree pulse. All right. And then what I would do is I would apply a pulse along the z-axis for some time tau. Yes, please. A pulse about the x-axis. That's the axis of rotation. All right. Then I let it evolve for some time. Then what I do is I apply a 180-degree pulse about the x-axis. All right, so I need more space, so let me redraw this. And let me simplify this a little bit or complicate this a little bit. So please treat this as a homework problem. I just want to see what happens on the block sphere. All right, please be attentive. First of all, apply a pulse along the y-axis, 90-degree pulse along the y-axis. A 90-degree pulse. Yes, please. 90-degree pulse along about the y-axis, followed by a pulse along the pulse along the z-axis. Pulse along the z-axis for time tau. All right, followed by a pulse along the x-axis, which is kind of thicker in time, which means it's a pi pulse, followed by another period of field along the z-axis through time tau. This is the spin echo sequence. Now immediately, will you be able to tell me what happened on the block sphere? I start here. I start at ket 0. This is my x, this is my y. What does the first rotation do? Where does the state land after the first 90-degree pulse? Right, it will land here. Correct? So it's going to come down through a 90-degree rotation and land here. Got it? Now it's landed at ket 0 plus ket 1. What's going to happen under the action of this z field? It's going to precess. It's going to fan out. Got it? Going to fan out. It's going to move in the equatorial plane because now this is the axis of rotation. It's going to go around on the equatorial plane. Suppose it moves through some kind of phase, some angle here, and my tau ends over here. This is my end of tau. This is this point here. Got it? Now what's going to happen if I apply a 180-degree pulse about the x-axis? This is my x-axis, this is my state. What's going to happen? From the east hemisphere, this pulse is going to go to the west hemisphere on the equatorial plane. So this pulse is going to come around, round, end up here. Like this. This is spin choreography on a block sphere. Spins dancing on a block sphere, doing tango on a block sphere. So it ends up here. Now what happens if I let it evolve, go around under the action of the z field for another equal amount of time tau? It's going to come back here. All right. Now why is this sequence important? If you have a detector along the x-axis, maximum signal will occur when this spin is also pointing along the x-axis, or it's moving close to the x-axis. Now NMR is very fragile. The signal strength is really precious because there's very little polarization in NMR. You want to get as much signal as possible. Now if you have a sample in which there are many spins, the last point, I promise. If you have a sample in which you have many spins, different locations, and you don't have a homogeneous magnetic field. So some spin sees a field of 1 Tesla, the other sees a field of 1 plus 1 millitesla, other sees 1 plus 1 minus millitesla, another sees 2 millitesla. So there's a gradient of fields. The field is inhomogeneous. So that means if you have a spin and it's going around in an equatorial plane, some of them will go faster, some of them will go slower. Now when you have some fast spins and some slow spins, you take a kind of a fanning out of spins, you take the vector, it's not evolving at all. I mean, the resultant is going to collapse. So you want to have all the spins together in phase. How would you do that? If you let this spin go around for some time tau, come back at an equidistant position at the back. This is an equidistant position because this time tau is the same as this time tau, and let it evolve, it's going to always end up here. A spin that has gone faster, suppose there is another spin that has gone faster, it moves further out in this time period tau, but a 180-degree pulse brings it back down here, and then another evolution through tau will bring it back into the original position. So all the spins that have spread out, that have fanned out in time, which are diminishing the signal, they are recombined. And when they recombine, the signal gets stronger. And that's how you preserve this precious resource of signal strength. You want all the spins to be in phase. That is the concept of coherence. And this is an example of kind of correcting for errors in quantum circuits. If you build a quantum computer and you're not able to correct for errors, your quantum computer is not going to work. You always have to come up with fault tolerant mechanisms to correct for errors. And by looking at the block sphere, you can actually look at different kinds of pulse sequences that kind of correct for errors. One example is, suppose I want to do a 180-degree pulse. And this is a homework problem. A 180-degree pulse from ket 0 to ket 1. So the ideal pulse goes from here to here. But suppose the engineer programs 180-degree pulse, but instead of 180 degree, it turns out to be 175 degrees because of calibration error. So the state does not go all the way down to the south hemisphere. So the way in which you can correct that is you do that erroneous pulse, do a 180-degree pulse, come back, and then do another erroneous pulse. You'll be closer to your final target. This is the idea of composite rotations. And I'll give you a homework problem on this. So in the next lecture, we're going to start our discussion of the somewhat simpler time independent Schrodinger equation.